Hello, in this video we'll see an additional parameter um, following the least square method video, of course. This parameter is called the linear correlation coefficient. So it's a standard in bivariate statistics. We have to see that. It's defined by a calculation by the division of the covariance of the pair xy by the product of their standard deviation. It's denoted with the letter R, which will appear like that, or the Greek letter R, which is pronounced rho, which could be taken as P, but which is a R. Well, anytime in absolute value, a covariance is less than the product of the standard deviations. It could be at some point equal to this product. But this fraction leads to a result that is between 0 and 1 anytime. But a covariance could be negative. So this result as a coefficient can be between -1 and 1. Okay, so it will always be like that. And if you find after this calculation more than 1 or less than -1, you made a mistake. So that's the first result that you have to know with this coefficient. So of course it's related to the linear behavior between variables. And that you have to know is that if your points in the cloud are exactly collinear, which doesn't happen in reality, but the limit case would be that, well, you will obtain a coefficient that is exactly equal to 1 or -1. Okay? If the points are not exactly collinear, but close to be collinear, your coefficient will be close to 1 or -1. Because two possibilities are created by the sign of the covariance. The standard deviations under that are positive, so the sign of R only depends on the sign of the covariance. A positive covariance shows a global trend of increasing of y with respect to x, and a negative covariance, a global trend of decreasing of y with respect to x. And you will see that again in the coefficient R. Well, if the coefficient is close to 1, it's considered as an interesting situation, but we'll see that we can comment on the value of R different ways. A criterion is that if R exceeds 0.95, we can consider that there is a very good linear correlation between our variables, a strong linear correlation. And in this case, maybe the linear model will be the most appropriate to model the cloud. Okay, so a first comment here is that this is not because your coefficient is very good, for example, 0.99, that the linear model will be the best to represent the cloud. Maybe a point cloud could appear very thin but a little bit curly, and then your linear correlation coefficient will be very good because the points are close to be collinear, but a linear model will be very, very wrong to make statistical predictions, okay? Because it's a slight curve, okay? It's slightly curly, and then if you draw a straight line and try to express the trend of the cloud by a straight line, maybe if you go far enough, your straight line will be very, very different from the result given by a curve that represents the cloud better. So the first point is that a very good linear correlation coefficient doesn't always mean that the linear model is the best model. Then we can have a look at several clouds and see that for the two on the left, you've got points that turn around a straight line correctly, let's say, so you will obtain, indeed, in this case, a good coefficient. So I don't know if in this graph it would be more than 0.95, but let's say it will be more than 0.75. So it's quite good. Of course, on the right, you can see other situations that will lead to a bad linear correlation coefficient because there is no way to model it by a line, okay, a straight line. So in the second situation and in the third one and in the fourth one, the coefficients will be bad, not close to 1 or -1. Well, Um, the comment here is that if by calculations you obtain a bad correlation coefficient, that doesn't mean that there is no correlation between the variables. There is a big difference between the second graph and the third one, because if in the second, you can see that the point seems gathered at random. Okay, there is no trend of values of y with respect to an evolution of values of x. Okay, if you take a little value of x or big value of x, there is no real variation at the growing or decreasing value of y. So there is no strong correlation between variables. In the third graph, there is a strong correlation between variables, but this correlation is not linear. That's all. You can see y decrease precisely, okay, with respect to x on the left, and then y begins to increase. So the point cloud seems to follow a curve very precisely. But this is not a linear correlation. So your linear correlation coefficient will be bad, though there is a strong correlation between your variables. So be careful, a bad correlation coefficient, linear one, could express both kind of situations. Okay, and the fourth one is equivalent to the second one. Below them, you've got equivalent graphs, okay, that shows trends that are opposite to the first line, but this is not very important. So you will obtain here a good coefficient, but negative, and for the three last graphs, a bad correlation coefficient. So let's go back to and let's sum up with our comments. A very good linear correlation coefficient doesn't always mean that the linear model is the best. A bad linear correlation coefficient doesn't mean that there is no correlation between your variables. And let's see a third comment with an additional graph to express what could represent a bad coefficient. So in this graph, the coefficient goes to minus 0.74, so it's not very good as a coefficient. But if you are looking to the shape, whatever the situation or the case, if you are looking to the shape of the cloud, you can see that this cloud um, seems to have an axis that is straight, okay? There would be useless to try to find a curve to express the evolution of y with respect to x here in this graph. So even if you don't have a linear coefficient that is good, maybe the linear model will be the best yet. Okay, so that's what the third comment. And so be careful with the value of your linear correlation coefficient. It's just indicator of something, okay? Are the points close to be collinear? But that's just a special case, okay? And in most cases, maybe a linear model will be very good to represent the global trend of the cloud. A last example, which is not based on the appreciation of the linear correlation, though it's very good, okay? So negative 0.9875, it's a very good correlation coefficient. You've got here the evolution of the wedding rate in France through time here, okay, 1974 to 1981 with respect to the evolution of the GDP, okay? PIB is in French, Produit Intérieur Brut, GDP, Gross Domestic Product, okay? This is the translation. So, As we can see, through time, okay, from one year to the other, the wedding rate in the population decreased and the GDP increased. And the way it increased this way and decreased this way follows a straight line, almost exactly accurately. So here it's just a coincidence. Okay, there is a very strong correlation between both variables, and plus this is a linear correlation. Okay, why not? But this is a coincidence because before 1974 and after 1981, the points seem gathered at random. Okay, so this example was just um, to tell us or to tell you that you don't have to make any confusion, or you mustn't make any confusion between correlation and causality. Okay, there is no cause and effect relationship from the GDP to the wedding rate in a country, and in France, for example. If you Google weird coincidences or weird correlations, that better, you will find websites that shows some coincidence like that, okay, that are funny most of time, and you will see that there are a lot of coincidences, but there are a lot of coincidences, maybe some hundreds, among a million or a billion crossing between variables that are made by computers, of course. So, well, just be here for the next video. Bye bye, and so on.